It's so frustrating when the tech we count on just fails.
Oh, definitely. It really throws a wrench in things.
Well, what if there was a way to build that software, with more confidence from the start?
That's where today's topic comes in.
Exactly. Today we're doing a deep dive into unit testing. It's this core practice in software development that's all about preventing those kinds of bugs.
Yeah, we're going to unpack it. Unit testing is basically how developers check their own work, like piece by piece as they go, trying to build in reliability. And the sources we've looked at, they really break down what it is, why it matters so much, and how developers actually do it, especially using this thing called JUnit.
Okay, so our mission today, really get a handle on how developers build up that trust in their code step by step, which hopefully means, more stable software for us, less pulling our hair out.
Fingers crossed.
All right, first things first, let's get basic. In software, what are we actually talking about when we say testing?
Fundamentally, testing is, well, it's a search. You're actively looking for errors, for defects, anything that's wrong with the software.
Like hunting for problems.
Exactly. It's like being a detective. But, and this is really important, the computer scientist Dijkstra made this point. Testing can show you that bugs are present.
Right.
But it can never, ever prove they're absent. You might find some, maybe lots, but you can't be 100% sure you found them all.
That's a key distinction. Finding problems, not proving perfection. Okay. Now, the sources mention a few terms. Failure, defect, exception, bug. Are these all just synonyms? Or is there a difference?
Casually, yeah. People might use them interchangeably. But technically, they can mean slightly different things.
Okay.
A defect is like the actual mistake in the code. The programmer's error. A failure is when the software doesn't do what it's supposed to do, often because of a defect.
Gotcha. Cause and effect.
Right. An exception is a specific kind of error that pops up while the program is running. And bug, well, bug is often the catch-all term people use for any problem.
Right, the common term.
But what's really fascinating from the sources is where these defects actually come from. Get this. 55% are apparently specification errors.
Wait, really? Over half from the requirement?
Yeah. Problems with the initial plan. Then 30% are design errors, how it's structured, and only like 15% are actual coding mistakes.
That's kind of mind-blowing. You'd think it would mostly be typos or logic errors in the code itself.
I know, right? It really shows how vital getting that initial understanding right is, more critical than the coding sometimes.
Okay, so accepting we can't zap all the bugs. How does unit testing fit into this picture?
Right. So unit testing is something developers do while they're coding. It's proactive.
During development.
Yeah, it's their way of constantly checking, does this little piece I just built work correctly on its own? The core thing is the unit test itself. It's a separate bit of code written just to test one specific small part of main software, usually just one method or function.
So super focused, like testing one Lego brick before you add it to the castle?
That's a great analogy. Yeah, exactly that. And these tests, they run in what's called a testing context. The developer sets up specific conditions, specific inputs, just to see how that one little piece behaves in isolation.
A controlled environment.
Precisely. And just briefly, there's this whole approach called test-driven development, TDD.
Heard of it?
That's where you actually write the unit test first, before the code it's supposed to test. The test basically defines what the code needs to do.
Whoa. Okay. So you define success before you even start building. That's interesting. Different way of thinking.
It really is.
Now, our sources also mentioned a whole bunch of other testing types. White box, black box, integration, system testing. Sounds like a whole ecosystem.
It is, yeah. There's a whole spectrum.
So where does unit testing sit in all that?
Well, black box is testing from the outside, like a user inputs, outputs, don't care how it works inside. White box is the opposite. You do know the internals, the code. Integration testing checks how different pieces work together. System testing looks at the whole application. Unit testing. That falls mostly under white box.
Because the developer knows the code.
Exactly. They wrote it. They know how it's supposed to work internally. All these types are important, but for this deep dive, we're really zeroing in on unit testing.
Right. Okay, so let's dig into that white box versus black box thing a bit more. Black box, you said, is like behavioral testing. Testing without knowing the insights. What's a big plus of doing that?
The main advantage is, well, it mimics a real user. The tester isn't biased by knowing how the code should work. They're just focused on, does it do what it's supposed to do from my perspective?
The user perspective.
Exactly. It can find usability issues, things that just feel wrong, discrepancies, and you don't need to be a programmer to do it. So you can get more people involved, maybe get a more objective view.
Makes sense. evaluating the experience.
Yeah.
But what's the downside? Seems like you might miss things if you can't see inside.
You definitely can. It's hard to design really thorough tests if you don't know the internal paths and logic. You might miss important edge cases.
Like weird scenarios.
Yeah. And if something fails, it can be harder to figure out why without seeing the code. Coverage can be a bit hit or miss too, and you might end up testing the same thing multiple times without realizing it.
Okay, so limitations there. Now, white box the opposite. Done by developers, people who can see the code. What's the key benefit there?
Well, because you can see the code, you can be really deliberate. You can design tests to hit specific lines of code, specific decision points, all the internal pathways.
More targeted.
Much more targeted. You get much better coverage of the code itself. And you can start doing this kind of testing, like unit testing, really early, even before you have a user interface. You can test the core logic.
Right, testing the engine before the car body is even on.
Yeah.
What about the challenges with white box, though?
It takes skill. You need developers, people who understand the code well, and the tests themselves are code. So when the main code changes, you often have to change the tests too.
Maintenance.
Yeah, that can be a significant effort, especially if the code is changing a lot.
Okay, so we have the definitions, the context, unit testing versus black box. Now, the big question, why bother? Why should developers actually spend time writing these unit tests? The sources give quite a few reasons.
They do. First off, they're usually pretty easy and quick to write. Developers can kind of knock them out as they're coding.
Right alongside the main code?
Often, yeah, to immediately check if what they just wrote works. And even though each test is small, you can group them into test suites. So you can run like hundreds or thousands of tests all at once.
Okay.
And the killer feature, automation. You write them once, run them again and again. Every time you change the code, run the tests. It's a safety net.
Catches regressions, right?
Yeah.
When you fix one thing and accidentally break something else.
Exactly that. It's huge for preventing regressions. Plus, there are all these frameworks and tools available like JUnit, which we mentioned. They make writing and running tests much easier.
So tools help?
Definitely. And the payoff. Less time spent debugging later, because when a unit test fails, you know exactly where the problem is in that small unit.
Pinpoints the issue.
Right. Which means fewer bugs escape into the wild, and you catch them much earlier when they're cheaper and easier to fix.
Okay, those are strong arguments. But the source also mentions some pushback, Why test my own code? No time. It's not in the requirements.
Yeah, you hear that sometimes. Things like, oh, this code is simple, it's obviously right. Or deadlines, no time for tests.
Dangerous assumptions.
Very. The obviously correct thing. Even the best developers make mistakes. Unit tests are your early warning system. And the time argument. You usually save way more time finding bugs early with tests than you spend debugging them later without tests.
Pays for itself, basically.
Absolutely. And, okay, maybe the spec doesn't explicitly say write unit tests, but the goal is always working, reliable software. Unit testing is just a fundamental way to help achieve that. It's professional practice, really.
Right. It's about building quality in, not just hoping for the best. Okay, so frameworks. We mentioned JUnit for Java, but the source listed others too. PHP-Unit, PyUnit. Seems like this idea is pretty widespread.
Oh, totally. Almost every major language has its own popular unit testing framework, usually following similar principles. It just shows how accepted and, frankly, necessary unit testing is considered in modern software development.
It's become standard practice.
Pretty much, yeah. These frameworks give you a structure, tools, makes it easier to actually do the testing consistently.
And JUnit is the big one for Java. Our source called it the most popular, adapted from something called XUnit. What's the background there?
Yeah, JUnit's story is pretty cool. Back in the 90s, a guy named Kent Beck developed this idea of automated testing tools called XUnit for a language called Smalltalk. Then a bit later, he was on a flight with Eric Gamma, one of the authors of that famous design patterns book, and they basically hashed out JUnit for Java right there on the plane.
No way. On a flight.
Apparently so. And it just took off, became absolutely central to things like test-driven development in Java. Now it's built into pretty much every Java IDE. Developers just expect it to be there.
Wow. And it inspired similar tools for other languages.
Yeah, that whole XUnit family of tools owes a lot to the original Smalltalk version and then the success of JUnit.
So it's influential. The source mentioned JUnit uses design patterns, composite, and command. Sounds a bit technical. Can you break that down?
Sure. Think of the command pattern like this. Each test case, which holds your test methods, acts like a command. It's an object that bundles up everything needed to run a specific test. The setup, the execution, the checking.
Like a self-contained test instruction.
Exactly. And the composite pattern, that's about test suite. A test suite can hold individual test cases, or it can hold other test suites.
Nesting them.
Right. It lets you build up hierarchies. You can have a suite for a whole module, which contains suites for submodules, which contain individual test cases for classes, lets you organize and run tests at whatever level you need. Very flexible.
Okay, that makes sense for managing lots of tests. Now, the source also listed some key JUnit terms. Fixture, test case, setup, teardown, test runner. Seems like the building blocks.
Those are the core concepts, yeah. A fixture is just the set of objects or data your tests need to work with. It's the starting state, the context.
A stage setting.
Good way to put it. A test case is the class where you define that fixture and write your actual test methods. Setup is what you do before each test runs getting the fixture ready.
Okay.
Teardown is the cleanup after each test, resetting things, releasing resources so tests don't interfere with each other.
Important for isolation.
Crucial. A test suite, like we said, is just a collection of test cases, and the test runner is the tool that actually executes all the tests in the suite and tells you what passed and what failed.
The director reporting on the performance.
That's it. Often you see the results as like a green bar if everything passed, or red if something failed.
Gotcha. And how does it know if something passed or failed? The source mentioned assertions, like assert equals assert true.
Assertions are the heart of the test method. That's where you actually check if the code did what you expected.
The verification step.
Exactly. Assert equals expected, actual, literally checks, is the value my code produced. Actual, the same as the value I expected. Assert true condition, checks if some condition is true. Assert null object, checks if an object is null, and so on.
And you can add a message if it fails.
Yeah, most of them let you add a string message. Super helpful for debugging. When something goes wrong, it tells you why the assertion failed.
Okay. And there was that assert equals with a delta. For floating point numbers.
Ah, yes. That's for comparing numbers like doubles or floats. Because of how computers store them, tiny precision differences can make a direct equality check fail unexpectedly.
Right, like 0.1 plus 0.2 isn't exactly 0.3 internally sometimes.
Exactly. So the delta lets you say, it's okay if they're not perfectly equal, as long as they're within this tiny tolerance range, the delta of each other, makes tests on floating point math more robust.
Practical. Handles the quirks of computer math. The source even showed JUnit assertions next to ones from UNIT, another framework. Looked pretty similar.
Yeah, the core ideas asserting equality, truthiness, nullness, they're fundamental. You find similar assertions in most XUnit style frameworks. The syntax might differ slightly, but the purpose is the same.
Okay, so putting it all together, when a developer writes a JUnit test class, what does it look like? The source mentioned a skeleton and talked about annotations, especially comparing older JUnit 3 with newer versions.
Right. The basic idea is a class full of test methods. Each method tests something specific and uses assertions, but how you structure it changed quite a bit between versions.
How so? What are the main differences, say, between JUnit 3 and 4?
Well, in JUnit 3, your test class had to extend a base class called test case, and your test methods had to start with the word test, like test addition. Yeah. JUnit 4 made it more flexible with annotations. You don't need to extend test case anymore. You just mark any method you want to be a test with at test. Much cleaner.
The at symbol thing.
Exactly. Unit 4 also added things like at test timeout to fail tests that run too long, and disabling tests became easier. Instead of renaming or commenting out, you just add an add ignore annotation.
Annotations seem much clearer. What about setup and teardown? The source mentioned at before, at after, at before class, at after class.
Those are key JUnit 4 annotations for managing the test lifecycle. In JUnit 3, you had methods specifically named setup and teardown that ran before and after each test.
Okay.
JUnit 4 uses annotations. At before runs before each test method in the class, like setup. At after runs after each test method, like teardown.
Got it. What about at before class and at after class?
Those run only once per class. At before class runs before any tests in that class start, and at after class runs after all tests in the class have finished. Useful for expensive setup or cleanup that you only need to do once for the whole set of tests, like connecting to a database.
Class level versus test level setup.
Exactly. And JUnit 5 refined these further with names like at before all, at after all, at before each, at after each, which are arguably even clearer, but the concept is the same, controlling the setup and cleanup around your tests.
So it's all about ensuring each test runs in a clean, predictable environment. Makes sense. Okay, so we've covered the mechanics, the how, But our deep dive ends by asking, what to test? Which feels like a huge question after all this.
It really is. And honestly, that could be a whole other discussion. But the general idea, you want to focus your testing effort where it counts the most.
Where is that usually?
Well, think about the core logic of your application, the complex bits, the parts that are absolutely critical for it to work. Places where a bug would be really bad.
High-risk areas.
Exactly. Test the happy path, the normal expected behavior. But also, crucially, test the edge cases, the weird inputs, the error conditions. What happens when things go wrong?
So testing assumptions and boundaries.
Precisely. It's about being strategic, identifying the most important units and writing tests that really put them through their paces under different conditions.
Okay, let's wrap up this deep dive on unit testing. We've really unpacked it, saw it as this vital practice for building quality software by testing the small parts first.
And we looked at the big benefits, catching bugs super early, cutting down that painful debugging time, and just shipping more solid code.
And we saw how frameworks like JUnit really help developers structure and automate this whole process.
Yeah, it really comes down to building confidence. Confidence in the code you're writing, piece by piece. It's an investment for sure, but one that pays off massively.
It really does make you think, though, when you consider all this effort developers put into testing, even for seemingly simple apps. It just underscores how complex software development really is and how much unseen work goes into the reliable technology we often just, take for granted every day.
Absolutely. There's a lot going on under the hood.
Well, thanks for walking us through that. Really insightful.